Welcome to lecture. In this lesson, I'd like to go over the algebra review. This is lesson 1 of a continuing series. So I'm going to start out with talking about some set notations and different notations that we can use to represent a set of numbers. And in this course, as we go through, we're going to be talking about mainly real numbers. But here's just different ways that we can represent numbers. We can represent them as a set. And here I'm going to represent this as the set W, whole numbers, equals, this is my little bracy, and I'm going to talk 0, 1, 2, 3. So W is the set of numbers consisting of the following 0, 1, 2, and 3. And the dot dot means I continue on. Now over here I've got this little symbol with the slash with the 0 with the slash. That's the empty set. So there's nothing in there in the empty set. Our list of integers, the set containing dot dot dot, continuing from -3, -2, -1, 0, 1, 2, 3, and continuing on. That dot 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 says to continue on. So here's some other notations that you may see as we run into different lectures. This little epsilon means it's an element of, so I can say 4 is an element of n. 5.9 is not an element of W. The little slash is not an element of. And this big C here is a proper subset of. So n, the natural numbers, 1, 2, 3, 4, 5, is a proper subset of the whole numbers. So the basic, what we've been using in here is called the roster method. The roster method is just, I'm going to list it as the actual things that are in the set. This could be anything. There's a set of colors consisting of red, green, and blue. Here's the set of numbers consisting of just 1, 2, and 3 only. If there's too many of it, I want to look for other ways to do this. I don't want to have a long list of numbers. And for instance, I'm going to use a set builder notation. If I wanted to list all the natural numbers less than 3, I would say this is read the set of all x such that x is in n, x is a natural number, so I can put clarifiers on there, and then x is less than 4, so 1, 2, 3. This would be the roster method, and this is the set builder notation for the same set, 1, 2, 3. So I'm going to get rid of me for the moment, and let's talk about the set of rational numbers Q. The set of rational numbers Q is the set consisting of all the numbers P and Q, P divided by Q, such that P and Q are in Z, the set of integers, and Q is not equal to 0. Here it's important that Q is not equal to 0 because I don't want to divide by 0. I'm going to find that that is just undefined for us, and we'll look at that later on. So here's the verbal interpretation of Q. The rational numbers can be expressed as a ratio of two integers where the divisor is not 0. So -3/7 is a rational number, and 6/1 is a rational number. 6, any whole number 6, or any integer could be considered as a rational by thinking of the bottom denominator as being 1. So all terminating and repeating decimals are rational numbers. So 0.937 I can represent as a rational by saying 937, the numerical part of this, and representing the denominator as 1 followed by the number of zeros. So this is the same as being dividing by 1,000. 3 decimals, 1,000. So 0.3, if I have a repeating decimal, I can represent that as 1/3, and there's a method for translating a repeating decimal into a fraction or a rational number. There's also other numbers called the irrational numbers. Pi, the 3.14 ratio of the circumference to the radius, 2 times the radius or the diameter. It's pi. Square root of 11 I can't represent as a repeating decimal or a terminating decimal or repeating fraction. So when you do this on your calculator, if I just go to my calculator and hit pi or the square root of 11, I get these numbers, but they're not exact values. These are just terminate wherever what the length of your display goes to, and your calculator set for significant digits. Here's our whole real numbers. This is what we're going to be dealing with many times in our lecture series. Here's the rational numbers. The rational numbers 1.62, 2/7, 1.437. And a proper subset of those is the integers. A proper subset is the whole numbers and natural numbers. So you can think of these as building out. We start with our natural numbers. We include 0. We go to our negative numbers to build our integers. And all of this is a proper subset of the rationals. Everything in here we can represent as a P over Q such that Q is not equal to 0. Now over here is the irrational numbers, and we want to consider the irrational things that cannot be written as a ratio of integers. So these two are disjoint, so none of these are over here in the irrationals. And here was our pi and square root of 19. Includes all non-terminating and non-repeating decimals. Those are the irrational numbers. And these two, this is all the irrationals and all of the rationals, which are subsets here building up, build up to the real numbers. They make up the real number system. And that's what we're going to be principally dealing with in this course. Set builder notation. When I want to talk about real numbers, and this is what we're going to kind of go from now on, I'm going to use a set builder notation, and I want to represent this. I want to start with here and then go through each one of these. Set builder says the set of all x's such that x is greater than a. When I use this x, I'm going to assume that they're real numbers, that we know what we're talking about, that we're in the real number system. Set of real numbers greater than a is how I just say that, if I just wanted to say it without all the set builder emphasis. Here's my a. I need numbers bigger than a, all the real numbers greater than a. So I write this as a number line going from negative infinity way over here to plus infinity. I'm going to start at a, continue on to infinity, and then another way I can do this is through interval notation. I'm saying a up through infinity, any number in here, a plus 1, a plus 2, a plus 0.75, a plus pi would be in here. And I have to be careful with this notation when I use the parentheses, say the a is not including, infinity is never included, but this looks very familiar if you're used to graphing as a coordinate, x, y coordinate. This is something different, and we just have to be careful of which one we're talking about. Here's the set of all x. That's x is, I'm just circled the equal to, x greater than or equal to a, and the equal to says we're including a. So verbal interpretation, the set of real numbers greater than or equal to a, and I draw it, and when I draw it to say that I want to include the a, I'm going to use this little brace right here, left brace, and it continues on. And the interval notation, I'm again going to use a brace that says include a. Up here with the parentheses says do not include a. The set of all x such that x is less than b. Less than is to the left. So if I have a number b, all the numbers to the left on our number line, all of our numbers as we go left were less than. Numbers to the right are greater than. Here's our representing it on our graph of our real number line. I kind of overlay this. I'm going to negative infinity. Here's that down here, negative infinity. But I'm going all the way up to b, but not including b because I don't have an equal here. So here's a nice table of kind of the different variations you could use. Set of all x such as x is less than or equal to b. There's the b, all the numbers less than, those are to the left. Include the b, and we always go from left to right when I build my interval notation. I'm going from negative infinity to b, bracket says to include b. The set of all x such as a is less than x less than b is the set of real numbers between a and b. There's the parentheses that say do not include a, do not include b. So those are just the numbers strictly between a and b. A and b not included. Now this also looks like a coordinate. This could be like 2, 3, where x is 2, y is 3. a particular point on coordinates, but this is an interval, and we just have to make sure that when we use this, we explain whether it's a coordinate or an interval. Here's a half open set of all x such that a is less than or equal to x less than b. The set of real numbers, they're greater than or equal to a is included, and less than b when we draw the graph. Before we didn't include the a, the bracket says includes the a, and here's the interval notation. Half open interval, the set of all x such that a is less than x less than or equal to b. The set of real numbers greater than or a and less than or equal to b. Here I'm including the b, the bigger number, the larger of the two. A is to the left, a not included by that parentheses, b is included by that little brace. Sorry, the bracket. Set of all x such that a is less than x less than or equal to b. The set of real numbers between a and b inclusive. The inclusive says that a and b are included. Here's my bracket a comma b, right bracket, and I close those because I'm including both a and b. And finally, here's that set of all real numbers that we're going to be dealing with mainly in this course. The set of all x such that x is a real number, irrational or irrational. It's denoted by this big uppercase R, the set of all real numbers. That means on that number line, I'm going all the way from negative infinity to plus infinity, and that's the interval notation, all the numbers in there. Negative pi, negative e, plus e, negative 1, zeros in there, all the real numbers. So here's a few exercises we're going to go through and just build on taking one representation of a notation of a real number set and two other ones. So if we were given, here's our real number line, there's negative 7 going to the right with infinity. If I want to do a set builder, I'm saying the set of all x such that x is greater than negative 7. Greater than is to the right as I draw. And here's our interval notation, our negative 7, comma, infinity. Both of these are parentheses because I'm not including the negative 7. In number 2 here, I'm actually given the set builder notation. The set of all x such that negative 7, 6 is less than x, less than or equal to 1/3. Negative 7, 6 is to my left, that's my left value. I don't have an equal sign, so I put a parentheses around all the numbers up to and including, because of that equal 1/3, I put a right bracket here, negative 7, 6 up to 1/3, right bracket. So here's an interval. I want to graph it. Negative infinity up to 6.7 included. There's my right bracket. It says include 6.7. And my set builder, the set of all x such that x is less than or equal to 6.7. Here is things that we will use to build set. Mainly we will be using this term, the union. We'll be using this a lot, but I want to speak about the intersection as well. If I've got two sets A and B, I have two separate sets A and B, I can build a third set that's called the union of A and B, and it's basically everything that's in A and everything's in B. And that includes those things that are in both A and B possibly, if there's something in common. And in this case, there's visually something there. It would include all of those. Only list each one of these numbers once. So if it is in A and in B, all I need to do is list those one. So formally, the union of the sets A and B, denoted A union B, is the set of elements that belong to set A or set B or to both sets A and B. Here's the symbol, the uppercase, a big uppercase U, and I read it A union B. The elements in A or B or both. We will have frequent opportunity to look at this, and this as well as we go forward. The intersection of sets A and B, denoted A intersect B, is the set of elements common to both A and B. So I have a bunch of A stuff, a bunch of B, a bunch of elements in B, but here all I want is the ones that are both common to A and B. That's that inverted U, big U, and I read A intersection B. The elements in A and B, they have to be both A and B. So given the sets A, B, and C, determine the union or intersection as indicated. So here's my A, here's my B, here's my C, so 3 sets given. And I want to form the set A union B. So I'm looking for everything in A. A's in zeros in A, zeros in B. I want to put my 4, 8, 12 because I know those things. And I need a 3, it's not listed, I put it in. 6 not listed, I put it in. And 9 is not listed, I put it in. 12 here, I've already got it in A, so I don't include it twice. So I just put the minimum set for A union B. Here I need to build up A intersection B. So here I'm only looking at the things that are in both A and B. So I'll go through, I find my 0. Is 0 over here? Yes, so I list it. 4 is in A. Is 4 also in B? No, so I'll leave that out. 8 is in A but not in B. I'll leave it out. 12 is in A. 12 is also in B, so I'll list it. These are the only things that are in the intersection. That tells me that 0 and 12 are in both A and B. Here's just another union between A union C. It's either in A or C, and I'll list them. The intersection, only 4 and 8 are common between A and C. I go through each one. Is zeros and A's in C? No. 4, yes. 8, yes. 12, no. And the ones that are yes, I leave them in. B union C, it's either in B or C. And then B intersects C, there is nothing in common between. 0 is not there. 3 is not in there, 6 is not in C, 9 is not in C, 12 is not in C, -2 is not here in B, 4 is not in B, 8 is not in B, so there's nothing in common. So I just leave this as my 2 braces, or I could either write that as the 0 with that line through it, the empty set. So here's some 3 different sets I'm using, doing set builder notation, and then I follow it up with here's the graphs. Okay, and what I'm going to do is list these things as here's the graph or set builder, and how do I form C union D? Well, if I look, it's anything in C or anything in D, and there's some overlap here, but that's okay. They're in both of them. So here it's everything all the way through negative infinity to plus infinity. Everything is included because there's overlap, and then this picks it up. How about C intersection D? C intersection D says it has to be in both. -1's in both, so I can start there. I keep going up until 9. There's nothing else past this, but here 9 is not really included. So I have to leave that out. And this is how I would do the set builder, the set of all x, -1 less than or equal to x less than 9. Here's CDF again. C union F, C and in F, or in F, what's in C or what's in F. That means I get to go all the way from negative infinity. -8's not in here, but it's in here, so I include it. And then all the way up to 9, but don't include it. C intersection F, C intersect, it's got to be in both, all the way from negative infinity, all the way up to -8, but I do not include -8 because of that parentheses. And I build it as the set of all x such that x is less than or equal to -8. Here's my CDF again on this slide. D union F. Here's my D, here's the F. It's either need to be in D or F before I include it in my new set. So here is my D, here's my F, and then there's a piece in the middle. So it's x greater than or equal to -1, x less than negative 8. D intersect F, there's a big thing that's missing in here all the way from negative 8 to negative 1. It has to be in both of them. There's nothing that overlaps. So again, that's the empty set. So let's start talking about a relationship called the absolute value. When I deal with a number inside this little vertical lines here, I'm going to consider that to be the absolute value, and I read it, the absolute value of x. Here's the formal definition. Let x be a real number. The absolute value of x is equal to the set of all x if x is greater than or equal to 0, and negative x if x is less than 0. So basically, if x is less than 0, this is a negative number, and a negative times a negative would turn it into a positive number. So we'll see some examples in just a second. So here's the verbal interpretation of what the absolute value is. If x is positive or 0, then the absolute value of x is just x itself. Absolute value of 7 is 7. Absolute value of 0 is just 0. If it's positive, I can just remove that absolute value sign because that's all I want is a positive number. If x is negative, then the absolute value of x is the opposite of x. I want the negative of whatever I start. It's a negative number to start with. I want to turn it into a positive, and the way I do that is multiplying a negative number times a negative number, and it builds it up into a positive number. Okay. So let's look at some other examples. Here, the absolute value of 2 is just 2, but the absolute value of negative 2 is also 2 because I'm saying negative 1 to remove this. Formally, I say negative 2 gives me the plus 2. Okay, and sometimes we want to consider this as the distance from 0. How far is negative 2 from 0? It's 2 units. And how far is 2 from 0? It is 2 units. I want both of these to be positive number. So here's an expression. Write the expression as equivalent expression without absolute value bars. So the square root of 2 minus 2, the square root of 2 would be certainly less than 2. So this would be a smaller number minus a bigger number. That would be a negative number, even without having to go to the calculator and plug it in. This is approximately equal to 1.414. 1.414 minus 2 is your negative 0.59. I want the absolute value, but I don't want to use these decimal numbers. So I analyze it. I rationalize that this is going to be a negative, so I remove this by multiplying times a negative 1. Negative times the square root of 2 is the negative square root of 2. Negative times the negative 2 is the plus. I distribute my negative 1 across there. That flips the sign, and you always want to write the positive sign first. If there's no sign, it's understood positive, so it keeps me from writing two signs. So 2 minus the square root of 2, and that's going to be our positive number. Here's some other expressions that we'll run into. Let's say if we have something z minus 5, the absolute value of z minus 5 divided by z minus 5, for z greater than 5. I can't do this division piece directly because this is in the inequality. But once I recognize this is bigger than 5, that's bigger than 5, this is going to be a positive number. This is like 6, 7, 8, 9, 10. So that's positive. I can just remove the absolute value. Z minus 5 divided by z minus 5. Any number divided by itself is just 1. So I can just represent this as 1. And then how about z minus 5? The absolute value of z minus 5 divided by z minus 5 for z less than 5. Z less than 5, that's going to be a negative number. So I go negative times that negative as parentheses to remove that. The z minus 5 is 1, but I have that negative. So this is negative 1 expression. This is positive 1 just by dictating of this is going to be a positive greater than 5, and this is less than 5. When we would like to represent a particular number that when once picked it will not change, we use letters like A, B, or C. So if I use an A, B, C, you're going to think of that as something that we're going to call like a parameter. It's a number that once we talk about this particular problem, it's going to be fixed. That x can take on any number within, let's say, the real numbers, if we're talking about the real numbers. Okay, but within that context of that problem, it can still take on many. So, for example, I'm saying x is less than a. Think all the numbers less than some number a. So this would be 1 or 2 or 3, but those x's are still variables. They could take on many numbers. So here is the distance between 2 points on a number line. Before I said the absolute value is just that distance from 0. How about if I want to talk about the distance between 2 points and I want them to be positive in each case? So I can write the distance between 2 points A and B on a number line is given to the absolute value of A minus B or B minus A, either one. One could be negative, but when I'm talking about the absolute value, it's always a positive number. So the distance between 2 points on a number line is the absolute value of their difference. I only want a positive distance. I don't want any direction indication, basically. The distance between 1 and 4, 1 minus 4 is equal to negative 3. The absolute value of negative 3 is 3. 4 minus 1 is the absolute value of 3. And the absolute value of 3 is just 3. And here's kind of the picture. I want to know how many units between theirs. 1 unit, 2 units, 3 units. And again, we can do this as expressions. And to remove that, I just need to put them in correct order to make it a positive number. So write an expression using absolute values to express the distance between 6 and 2 pi on the number line. That's 6 minus 2 pi, or the absolute value of 2 pi minus 6. This is like 3.14, so 2 times this would be minus 6.2. So this is negative. So I multiply times the negative 1 to make it 2 pi minus 6, or 2 pi minus 6. This would be a positive number. This is 2 pi is a little bit bigger than 3. 2 times 3 is something bigger than 3 is a little bigger than 6. So there's our 2 pi minus 6. So when we start dealing with numbers for our algebra, we're going to simplify expressions as we start going through here. We're going to have to kind of go through some order of operations. So our step 1, when we simplify expressions, we're going to look for things within parentheses and other grouping symbols. Brackets, braces. These include absolute value bars, fractions bars, radicals. If nested grouping symbols are present, start with the innermost symbols and kind of group those, and then we'll work out from those. Then we'll evaluate expressions involving exponents. So if we have some grouping with the exponent, I would want to do the grouping inside, then the exponents. Make sure I take care of all my exponents before I can add or subtract. Multiplication or division in the order in which they occur from left to right. And then perform addition or subtraction in the order in which they occur from left to right. So here's an example. I want to simplify this expression. 7 minus, I've got a left brace, 8 plus 4 times, left bracket 2 minus 5 minus the square root of 64 squared. And then I close those up. So here is here's the solution that they're giving you. And they want to go through these pieces. I want to start working inside the innermost grouping symbol. That's the 5 minus the square root of 64. Square root of 64 is just 8. So I've got my 5 minus 8, that's my negative 3. I want to do any exponents first at that level, that grouping level. So this is 9. 2 minus my 9 is my negative 7. So now I can do the 4 times that, the negative 28. Then plus my 8 gives me the negative 20. 7 minus a minus 20, that's the 27. 7 plus 20. So here's some things that I'll run into. Division involving 0. I can't divide by 0, that's undefined. So, and to investigate division involving 0, consider the expressions 5 divided by 0, 0 divided by 5, and 0 divided by 0, and their related multiplicative forms. So division by 0 is undefined. Anytime, we'd always check. We just said a number divided by a number is equal to this because this times this was equal to the number. So 5 divided by 0, if I said this was equal to n, my check would say, oh, well then n times 0 should be that top number. But in this case, no matter what n we would pick, we would end up by 0, not 5. So there's no number that when I multiply by 0, I see it. So there's no number n for this. 0 divided by any non-zero number is 0. So this is easy. 5 times 0 is 0. 10 times 0 is 0. These are always a true statement. And then 0 is indeterminate, cannot be uniquely determined. And this concept is investigated more in detail in the first course in calculus. But basically, if I said 0 divided by 0 is equal to n, that would imply that n times 0 would be equal to 0. But that's true for all n. No matter what number we would say, that's equal to 0. So therefore, the quotient cannot be uniquely determined. So again, when we use A, B, and C in general, we do not expect these values to change within the context of a problem. We call these numbers parameters, and variables, on the other hand, may take on different values within the context of a particular problem. X, Y, Z is usually some of the things that we'll use, but it could be others. So how do we handle addition when I have this variable? If I'm talking about addition, then I'm going to use this. I'm just going to add these up. X plus X plus X, that's 3X or 3 times X. Just like if we had apples or oranges, I've got another number. This could be 2 plus 2 plus 2. Well, that's the same thing as 3 times 2, or 6. But I don't know what this number is, and I have to wait to find out. Somebody has to give me that number, but I'm going to do all the operations up till then. I use the shorthand notation of 3X. I just add them up, put that number in front, and then I just do the X. Multiplication, I use a little different terminology here, a little symbology. X times X times X. If I multiplied X by itself 3 times, I represent whatever this number is, and this exponent tells me how many times I need to multiply it by itself. If this was a 2, I just multiply X times X. So if X is 3, 3 times 3 would be 9, and X cubed would be 3 times 3 times 3 would be 27. How do we handle division? Well, 6x divided by 2y. I really write this division as like a fraction. Okay? I'm looking here, and then just like we did in fractions of arithmetic, I want to cancel out any common factors. So is 6 divided by 2? Yes, 6 divided by 2 is 3. 2 divided by 2 is 1. So I've divided out the top and the bottom by this number. X I can't do anything with. Y I can't do anything. So it's 3x divided by y. It's the result of that division. What about 6x divided by 2x? Here again, the 6 divided by 2, that was my 3. X divided by x, no matter what number I've got, if I divide it by itself, I just get 1. So x divided by x was 1. So here's just the result of my 6 divided by 2. Let's talk about signed arithmetic, subtraction, and addition. Think of all subtraction and addition problems as signed arithmetic. Same sign. If I've got two things of the same sign, I just add them and keep that sign. So 3x plus 2x, same sign, that's understood plus. That's 5x, keep the understood sign. Keep that sign, which is the plus. Here I've got a negative 3x and a negative 2x. I just add them and keep the sign, which is the negative. If signs are different, I'm just going to do a subtraction process just like I've always done. But here, because they can be in different orders, I'm going to do this with the same way. I'm going to do the larger. I'll take the larger, subtract the smaller number from it, and then whichever the sign of the larger, that's my result. So here, two different things. 5x minus 2x, 5 minus 2, they're different signs, plus and minus. 5 minus 2 is my 3. The sign of the larger number is plus, so I just keep the plus. I understood the plus, so if it's leading plus, I just drop it. I understood that. Here in negative 5x plus 3x, the larger is negative. is negative. I'm going to get 5 minus 3, the larger minus the smaller, which is 2, but I'm going to have that negative 2 right there. So terms and coefficients. Here's the terms. Here's the coefficients. Okay, I can consider each one of these things as the terms. So here, from here, the 12x squared y5 plus, I can do that in the negative, plus 9.2x y3. So I've got a couple of different terms, and these numbers in front of it, I'm going to consider the coefficients. So I've got 3 terms in here. So let's talk about the properties of real numbers. We need these to be able to handle all of our algebra as we go forward. And I'm going to use this to isolate some things. So I have this property that is called the community property of addition. And basically, if I've got 2 numbers, it doesn't matter which order I write them in. If I'm adding them up, 2 plus 3 is the same thing as 3 plus 2. Okay? And one of these could be an x. 5 plus x is the same thing as x plus 5. And I'll rewrite those ever how I need to at the moment at whatever problem I'm working on. Multiplication is also commutative. A times b is equal to b times a. So 2 times 3 is 6. That's the same thing as 3 times 2 would be equal to 6. And if I have something x times 5, I always like to write my coefficient out front. So that's the same thing as 5 times x. The associative property of addition says if I'm adding up multiple numbers, I can pick any 2 of those, add those, and then add up the third one, and it doesn't matter which one I do. So I could add up my a plus b first. That's what's telling you. Remember our grouping? So a plus b first, and then a c. So let's go 1 plus 2 plus 3. So 1 plus 2 is 3. 3 plus 3 is 6. And if I add it up to 2 plus 3, I get my 5. And then add up the 1, I get the 6. And if one of these are a variable, I can kind of group them as I needed. So if I got 4 plus 3 plus 6, I can group my 4 plus 3, that's the 7, and my x I can wait till later. So this is 7 plus x. How about the associative property of multiplication? 3 numbers, a times b times c. And the very same thing here, I can group the first 2, do the multiplication and then the third, or do second and third multiplication and then multiply times 1. And this is really how I've done both these 2 numbers. This is how I've always done addition or multiplication, and you have too. We just pick 2 numbers at a time and we start either adding them, and in the case of multiplication, I just pick 2, multiply, and I handle them times 2. Addition has this identity property. There's an identity element, 0, and basically I can add 0 to anything and I still haven't changed it. So if I have some number a like 2, 2 plus 0 is still 2. Doesn't matter which way because we can commute these 2. I can put the 0 in front or the 0 at the end. They're both a. And 0 I can add to anything and not change itself. I can insert 0 on either side of this equalities. Identity property of multiplication says is the 1, the identity element is the 1 is for multiplication. Here I can stick in a 1 anytime I need it. A times 1 is a, and 1 times a is a. And that's why I kind of, anytime the coefficient is not written, I understood that coefficient to be 1. There's our inverse property of addition. That's our negative a. So we have, for any number a, we've got a negative, and a plus that negative a is equal to 0. Negative a plus a, I can commute either one of these things, I still get 0. So if I wanted to change a side, turn it into 0, all I have to do is just say a negative 5, that gets rid of that piece of it as to 0. Okay. But later on, we're going to have to be careful when we use this in equations. If I do it on one side, I'm going to have to do it on the other side to maintain. The inverse property of multiplication, that's just 1 over a. So for any number, the reciprocal is the identity element. Okay? The product of any non-zero number and its reciprocal element is the identity element 1. Okay? A divided by a is simply 1. 1 times a is a. Okay? Either way you want to consider that. Here's a distributive property of multiplication over addition. I'm going to use this frequently as throughout the course. Anytime I have sum A times the quantity, the grouped B plus C, it is the very same thing. If I want to get rid of these parentheses, all I have to do is distribute A over B and A over C. So that's just, by definition, A times B plus A times C. So if I say 5 times the quantity x plus 3, 5x plus 3 times 5, that gives me 5x plus 15 to remove the parentheses. So although the distributive property is used to add and subtract like terms, it is tedious to write each step. Adding or subtracting like terms can also be done by combining the coefficients and leaving the variable factor unchanged. So I'll look at common terms. I've got common here is x squared, x squared, x squared. All I'm going to do is just go add 14 minus 1 is 13 and rewrite them. Okay, so this is simply what we're going to do. Instead of having distributive property and try to group all of them together, we're just going to recognize this fact. Got 8 of them, 6 of them, so I must have 14, but I take away 1, I've only got 13. So 13x squared. Here's a little exercise in combining like terms. I'm going to look for anything that has c to the 7th d. These has to be all the parameters or variables have to be the same. All the exponents of the corresponding has to be the same. So c to the 7th d and cd to the 7th are not the same. C to the 7th d, here's c to the 7th d. So all this and this is the same. I'm going to group these two. I'm going to combine them. 1/3 minus 2/5. So there's my grouping here times c to the 7th. And then I got cd to the 7th 1/2 minus my 2. I group these together. And now I'm just going to add the coefficients. Give me my LCD, the common denominator of 15. So I need to have this one times 5 over 5. We'll look at this later. 3 over 3 to get my common denominator of 15. Once I have a common denominator, then I can add the top. So this is just my negative 1/15 c to the 7th d. Here I needed this over 2 to get a common denominator. So a 2 over 2, the 2 is understood over 1. So 1 minus 4/2 minus 3/2 c to the d to the 7th. So again, we're just looking at examples of clearing parentheses and combining like terms. We're going to be using this throughout. These are just our drills to get used to simplifying things, clearing them when we need to, combining like terms when we need to. So if I have this expression, I'd like to kind of group all these things together. First of all, if I'm looking at my order, anything in the parentheses I need to clear, I don't see anything. Now I just need to distribute. Start with my 5, there's nothing there, and I'm going to rewrite this. So my -2, I need to distribute over my 4c, my 8d. -2 times 4c minus 8c. -2 times -8 is plus 16d. And then I've got my 3 minus 3d plus c. So my -8c plus c is my -7c. 5 plus 3 is my 8. And then 16d minus 3d is 13d. So that's my simplified version. They're all different in here, and then I just have that's as simplified as I can get it. So we're going to talk models, frequently building models throughout the course, or just simplifying models or using them. So an algebraic model, if I need to write something, here's how I would do it. So let's look at this one. The maximum recommended heart rate in for adults is the difference of 220 and the person's age A. Write a model to represent an adult's maximum recommended heart rate in terms of age. So the M is the difference of, so that would be 220 minus A. So M is equal to 220 minus A. The word difference implies subtraction in the order given. First and then the second. That's the order, the difference of this and this. B is after eating at a restaurant, it is customary to leave a tip T for the server for at least 15% of the cost of the meal C. Write a model to represent the amount of the tip based on the cost of the meal. Our C is the meal cost, and 15% doing percentage multiplication 0.15. I changed this to a decimal, moved 2 places to the left. So T is greater than or equal to 0.15 C. At least 15%, that would be bigger than or equal to those. Here, Jake is 1 year younger than Charlotte. So write a model for Jake's age, J in terms of Charlotte's age. So Jake is 1 year younger than Charlotte, so whatever Charlotte's age is, take 1 away from that, and that would be Jake's age. Write a model for Charlotte's age, C, in terms of Jake's age. I could do this directly and then solve for C, or by knowing, well, if Jake is 1 year younger, Charlotte must be 1 year older than Jake, so Jake plus 1 is Charlotte. So that's our end of our lesson 1. I hope you found it informative, and we will join you next time.